Howdy. This video is Graphing Rational Functions 2. And its purpose is to show a more advanced example. And the example is advanced not because the analysis is more difficult, but because it's going to have a couple of extra features that we haven't seen before. One of them is a slant asymptote. This material will not be on your quiz tomorrow. However, it's interesting and it's useful. We're also going to talk very briefly about a couple of coming attractions. Specifically, we're going to talk about features of the graph that we can see are there, but we don't know how to find yet. Specifically, maxes and mins. And so I want to consider the function g of x equals x cubed minus 9x all over x squared minus 4x plus 3. And we want to sketch this rational function using our basic framework of finding excluded values, classifying them with a limit, finding horizontal asymptotes, and finding zeros. So we're going to use the same framework we did before. And so to find excluded values, we set our denominator equal to 0. And fairly quickly find that we have two excluded values, which are x equals 3 and x equals 1. And we're going to test each one of these with a limit. We take the limit as x goes to 3 of g of x, which is x cubed minus 9x all over. I'm going to go ahead and write the factored form of our denominator here. And when we do, the form of that limit is 27 minus 27, which is 0, divided by 0. And this tells us that we have a common factor. If we find it. Specifically, I need to factor the top here. And I observe that the top has a common factor of x. So I can factor out that factor, leaving me with x squared minus 9, and x minus 3 equals x plus 3. There's my common factor of x minus 3. And when I cancel it, I get a 2 for bonus. I get, first of all, the value of the limit, which is going to be 3 times 6 over 2, or in other words, 9. But I also get a reduced fraction that I can now use in place of g of x. And so when I test it, I draw the conclusion from my analysis. Since I got a finite value here, I conclude that my graph as a whole at x equals 3 and with a y value of 9. If I now consider the limit as x goes to 1, using my reduced fraction in place of g of x, then I can quickly see that the form of my limit is 4 over 0, indicating that I have an infinite limit. So I do the analysis. As x goes to 1 from the left, as x goes to 1 from the right. And you guys can do the sign analysis yourselves and see that this limit is going to come out to negative infinity. And this limit is going to come out to positive infinity. So this allows me to conclude that there is a vertical asymptote at x equals 1. So that's all very good. What about zeros? Sorry, what about horizontal asymptotes? When we consider the limit as x goes to infinity, using my end model analysis, this gives me x model. Notice that x times x is x squared, x minus 1, the end model is x. So this is the limit of x goes to infinity of just x, which is positive infinity. This means that my function has no horizontal asymptote off to the right. And the same kind of thing happens as x goes to negative infinity. When I replace g of x or its reduced fraction in the model, I get now negative infinity as x goes to negative infinity. And this means that for very large x, my graph is going to go up. For very negative x, my graph is going to go down like that. Finally, we're ready to find zeros. And so we set our reduced fraction equal to 0, which allows us to conclude that the denominator, that the numerator is equal to 0. And I get two zeros, x equals 0 and x equals negative 3. We need to do a quick check to make sure that those are not any of our excluded values, and they are not. So we have two zeros, x equals 0 and x equals negative 3. Okay, so this is all fine. We're ready to graph. So we're going to take that information that we got and summarize it. We found that we had a pole at 3, 9. We found that we had a vertical asymptote at x equals 1 with the limit as x goes to 1 from the left being negative infinity, and the limit as x goes to 1 from the right being positive infinity. We found that we had two zeros, x equals 0 and x equals negative 3, and no horizontal asymptotes. In particular, the limit at as x goes to positive infinity was positive infinity, and the limit as x goes to negative infinity was negative infinity. And this is enough information to do our graph. Here comes the asymptote. So, and we are going to go down on the left and up on the right according to the information from our limit. We're going to plot two zeros at x equals 0 and x equals negative 3. And we are going to plot our pole at 3, 9. 3, 9. That's quite interesting. And so now we're ready to do our graph, making sure that we go piece on the right here. We're going to come down from infinity. We have to actually go back up through that hole and out to positive infinity next time. And for this graph right here, we need to go up, hit 0, come back down, and go out to negative infinity like that. And this is the graph of our function. So this is all very fine, and there's nothing about this that's amazingly difficult. It was just a little bit weird to have no horizontal asymptote. And it was also a little bit strange here that we had to turn around and go back. Now, what I want you to observe about this graph is that it appears as if this line right here is functioning as an asymptote for the graph. And in fact, I claim that the equation of this line that is the asymptote is the line y equals x plus 4. And I'd like to show you how I come to that conclusion. Remember that the original g of x was x cubed minus 9x all over x squared minus 4x plus 3. And what we did was to factor that, observe that except for x equals 3, that g of x is exactly equal to x times x plus 3 over x minus 1 when x is not equal to 3. Okay, so that's all good. Now what I'd like to consider is the information that we get by dividing. If I divide x minus 1 into the numerator, which is x squared plus 3x, right here. Since I'm doing long division, I'll give myself a plus 0. Then I end up with something very interesting. X goes into x squared x times, multiply, and subtract. X goes into 4x 4 times, multiply, and subtract, so that I get a remainder of 4. Now here's what this means. This means that my function x squared plus 3x over x minus 1 is the same as the quotient x plus 4 plus the remainder of 4 over x minus 1. Think about this. What I just said right here is that this fraction right here is equivalent to this function plus this fraction. And you can get yourself a common denominator for the right-hand side and see that this is so. Okay. Now how does that help us? Here's the next thing that I want to observe. I want to observe about the remainder term, that as x goes out to infinity, that the remainder term goes to 0, which means that for very large x and very negative x, g of x, or the reduced fraction for my g of x, will approach the line y equals x plus 4, this line right here, because this term is going to 0 for very large x. And so what we have discovered is the very first instance of what we call a slant asymptote. To find that slant asymptote, we divided and observed that all of the terms right here, the remainder term, is going to go to 0 as x gets very large. There's one more thing about this that I just want to point out, but we're not going to do any analysis on at this time. And that is that right here and right here, we have the largest and smallest, locally largest and locally smallest points. I'm going to call this a local maximum for the curve, and I'm going to call this guy a local minimum